We have first at the stage Mr. Robert Griffith. Robert is Director of the Green Roof Association of Australasia, specialising in green infrastructure on roofs and walls, as well as being a horticulturalist and an environmental scientist. Robert consults and installs projects that combine stormwater management, energy conservation and aesthetics. He has had guest speaking roles in Singapore, Dubai, Stuttgart, Beijing, Kuala Lumpur, as well as worked in the Middle East, Europe and Asia. Robert has managed and won 10 state and federal awards, including the Back Zero Award for Green and Golden Belt Frog Habitat in the Sydney Olympics. I'd like to introduce Robert to the stage.
Thanks, guys. Okay, so I think I just down arrow down. Is that how it works? That's it. Down arrow, is that what I'm using?
No.
Oh, mouse. Sorry. Looking at urban stormwater, that's what the topic is here, obviously. And I'm just looking at point source stormwater from where it starts. So the rain falls on the building and it's starting straight away. Keep going. So extreme urbanisation is really causing a problem. We had 7.46 billion people living in cities in 1950, and 2045 we're going to have 6 billion. So a big difference, and air pollution, floods and heat island effect are all part of what green roofs and what the problem we face is. So all greens in cities is a solution, and we've got a few different examples there of some designs in Paris. There are other projects here in Eco City in China, which are going ahead. And China's going in leaps and bounds on some of this green work, which is interesting to see. And I know they have lots of other problems, but they're the sort of country that are just doing stuff. And then when it comes to Paris, Amsterdam, Stuttgart, where I work, Chicago, New York, these cities are all have got policies in place now for green roofs and for stormwater management particularly. There was a little bit of talk before about the creeks that we're looking after in Sydney. The urban stream syndrome and flooding is obviously a big problem. I don't need to go into too much details because there was quite a bit given at the last talk by Phil. But high flows, incising creeks, and also changing the chemical properties of the water to stop the crustaceans and the invertebrates, which then stop the fish. So basically, we've got no platypuses, as he said, and we've got no fish either because of that. And green roofs are a tool to fight climate change. So I'll go into a little bit more detail about that and how that's proposed. But there's lots of examples of green roofs there on roads, on nature strips, as well as rooftops. So how do we know whether a green roof is performing well? So essentially, green roofs will perform differently in any climate. So every city around the world has a different climate, and they need to be adjusted to that. And then the main factors are the heat transfer model, which is basic physics, I guess. It's temperature, wind velocity, how much rainfall, and so forth. And those are different in every city in the world, and including, if you look at Sydney, Penrith is vastly different to the CBD, and Blacktown's about halfway between. So in rainfall, you've got 1.2 metres of rainfall in Sydney, you've got about 600 mil, I think, in Penrith, and about halfway between that in Blacktown. So that different rainfall events will mean you need a different type of green roof in each application, and that can be modelled. So I work with a couple of different companies. Knauf Insulation are a big sponsor of mine, and I'm looking at Urbanscape. I'm going to show you a few things about that. I'm also working with Semper Green, and they put together another model called Purple Roof. Don't ask me why it's called Purple Roof. There's no real good explanation. But these are a typical example of a purple roof. This is just plants growing very well on a roof. There's a nice pattern, it looks good, but it's actually a stormwater detention system. And I'll keep going. So on retention, green roofs have been known for a long time to provide good retention of water. So they hold the water up there, the plants transpire that water, they use the water. But the problem with it is, and for the stormwater engineers, which I'm sure some of you are, is that retention is only good if it rains the next day. We have a problem because once the medium is saturated, the next day that water is going to go straight through the system. So it's not really doing any detention. So I haven't got a whiteboard here, but and you guys would know how to do this a lot better than me. But if a drop of water lands on the top of on top of a mountain and it has to get down to a river at the bottom, you guys have got some calculations to work that out, but it's pretty well designed on, okay, how steep is it from there to there? What is the distance between there and there? And then what is the friction between there and there to slow that water down? So that's the model that we're using in green roofs, and that's the difference between retention and detention. Retention is it's holding the water there with the use of the plants. The only way that water can really go is through transpiration or drainage, and detention is actually holding the water there for a longer period of time, which is what all your stormwater detention tanks and so forth do. So we can do that with a green roof, and I'll explain that a little bit further. So just a demonstration. This is a product here that is part of the system, and this is the Canal Urbanscape product. So here we've got a 20 mil layer of rock wool, and this is 100% made from rock, so it's heated and then spun into a wool. And that particular product, if I have, so that's an A4 piece, 20 mil thick, and if you want to work out the cubic measurement of that, I think it's 1.3 of a cubic metre. So I'm going to pour a 0.1 of a, not 0.1 of a cubic metre, I'm going to pour 1 litre of water onto this, and hold it so I don't drop it. So this system okay, I've lost a bit because I had it on an angle. So that's the litre, okay, so it's just starting to drain, okay. The idea of this product is it holds 85% of its volume in water. Now this water is available for the plants. In Australia and America where we use this, we put a small layer of soil on top. It's very light because it's only 20 mil thick, and you can grow great plants on this. If I have 50 mil of soil on top of this, I can grow a very nice low green roof garden, ground covers, succulents, and some native grasses and things like that will grow very well in this. And it'll hold that amount of moisture. Now, as I said to you before, that's retention. So that's holding that water for the plants to use, and it's a very good way of growing green roofs. Really easy to install and so forth. It comes in big rolls and you just roll it out like turf, and you can make a green roof that's very light overall. So that's a little demonstration of the Urbanscape product. This is a green roof made from that product. It's in New York, and this water is detained before it goes into the Hudson River. And they had to have, again, with the rules and regulations in New York, they had to put this roof in to allow that development behind it, which is a large residential development. So, by the way, the dark green areas here are actually artificial grass in there for people to run their dogs around in. But these ones here are all green roofs, and they're doing a very good stormwater detention system. Another example of a typical green roof that is very common overseas in Europe and America. More examples, one of the largest hospitals in the world, Norway, green roof. So all these are designed for both insulation, heat island effect and stormwater control. Now, the software that runs this, I've got a couple of different software solutions. Sempergreen have developed this system here, which basically is just a web-based thing. You say, what's my soil depth? What's my mineral wool depth, which is that product down there? And the conventional drainage system. And out of that model there, and those are all adjustable with the plus and minus signs, I get stress days. So basically, I've got 81 days there that I'm going to have to irrigate that job because the plants aren't going to survive. And over here, I've got precipitation of 1,111 millimetres per year. I've got 667 through evapotranspiration leaving that job, and I've got 44% runoff. So this is not a very good green roof, by the way, because I've only got 100 mils of soil, I have no mineral wool, and I have a drainage system. So then these have all been modelled, all these results that you've got here, and it's been modelled for all sorts of climates around the world. So they've developed this, it's a 40-foot container, and they've got these modules which are 1 metre by 8 metres by 1 metre wide, which get slotted in. Then they can have any rainfall event you want in this system, and it'll work out how much water will drain out of the system. So that's the sort of field testing, if you like. Then this same model, so pretty much we've got the same roof build-up, and here these stress days I was telling you about, these periods of time in the red here where we need to irrigate this roof. We've got temperature and humidity being calculated. The blue ones on the top are rainfall events, and that's for Sydney. Okay, so this is actually 20 years of data of every rainfall event in Sydney, and then they're averaged out. So that's what they've worked that through on, and that's all adjustable. So here we're just saying that these are stress days. The purple ones are runoff days. So 1, 2, 3, 4, 5, 6, 7, 8 sort of runoff experiences without any mineral wool and with 100 mil of soil. If I put 75 mils of mineral wool and 150 mils of soil, the yellow ones are showing the changes that have occurred. So I've got less stress days. I've still got those 8 runoff days. So we've got a roof that performs, except for 8 times a year, it doesn't let any water out of the system at all. But those 8 times a year are a problem for stormwater engineers. They'll say, well, we still need a detention system because on those days the water's going to run off and I've got a problem and I'm not going to meet council requirements. So they modelled, this is Mexico Airport, and they used this system, they developed this system actually for this job, which was a massive job. I think it's about 5 hectares of plant material on that roof. That job didn't actually occur yet because the Mexican ran out of money. But that's the new airport design. And what they worked out there is this is the rainfall events for Mexico, and you might think Mexico's hot and dry. Well, it is, but it's monsoonal. I haven't actually been there, but for some of the views that have been there would know. They get all their rain between here and here, and it's massive. Now, if you had a system like I proposed without a detention factor, the roof would start leaking here in this month, and it would just keep leaking the whole way. Every time it rained, all the water would run out of it. So that's not going to be a detention system that you need. The reason I'm harping on about this is because green roofs, traditionally, they go, well, they're good for retention, but they won't do detention, so we still need a detention tank, so I've got no reason to put a green roof on. We'll just do it with a detention tank. Now, green roofs have a lot of other benefits, that I'll touch on briefly. So here we've got, same graph again, but we've got those 8 events where too much water is coming off. And here it is in a different form. We've got 35 minor retention events, 45 soil will just look up, 45 rainfall events through the year. Soil will look after completely. They're minor events, so they don't really count. Major retention, with the mineral wool added, we fixed 25 more events through the year. Still got 10, I said 8 before, but there's still 10 that haven't been fixed with the system that we've got. So we go one step further, and we put a detention layer in. Now I was saying before that that the difference, I'll just slide that in a second, but the difference is that the distance between the water's got to flow and the slope that there was. The next thing was lost it for a second here, but we've got a normal roof here, we've got one with mineral wool in here, and then we've got a detention layer in here. Now this detention layer, which I'll find in 2 seconds, is basically a 5mm layer of nylon, and when the water hits it, it slows the water up. And I've got some examples of what will happen with that. And when you have a normal green roof, water doesn't, if you get 10 mils of rain, it doesn't just run through your roof like that. It actually runs down through sections. as you can see there. So it runs down through the soil unevenly. That's just how soil works. And then it still runs down unevenly, and some of the water will run through almost immediately straight into your drainage system and out. So you've got water going through the system immediately going out. Here you've got a mineral wool layer which is helping that system because the water goes through that slower, and so it fills up. And then, well, that's the same thing there. And then when you've got a detention layer in it, again, water's going straight through. But when there's a detention layer, it's filling up the detention layer, and what that's doing then is filling up the whole soil media. Now, I've done farming in the Middle East, and where they do flood irrigation, the best way to irrigate plants is to actually flood the whole area, and you fill up all the pores, the macro pores in your soil, and that water stays there for quite a few weeks for the plant material. This is what's happening here. You're holding that soil up, you're slowing it down, and all the pores of the soil are getting filled up, and therefore you're retaining that water for longer. And so that's basically showing the same thing. That's completely full. And so you've got a lot of water there that's held in suspension for a short period of time. Now, why I'm saying that is because tiny events, storm events, no problem. If you've got gallons, 100 gallons in 60 minutes, that storm event is long enough to not go above this red line, which was, say, local government would say you cannot release water quicker than that on your subdivision or development site. This is your target. Now we've got 100 gallons in 45 minutes of storm water. Here we're starting to peak over here, and we've got about a third of the water leaving that site quicker than you're allowed to. So it's no good. 100 gallons in 20 minutes, you've got half the water leaving the site quicker than it should, no good. And if you've got a massive storm here, 100 gallons in 10 minutes, you've got 3/4 of the water leaving that site prior to what it should. So what you need to do with all these is you just need to get that bit of water there. So you've just got to slow that water down that little bit longer. All you've got to do is add a bigger case in that case there for that storm event. So you need to stop that water leaving that building that way. And this is a graph that comes out of the software that basically shows that's your storm event. All the other systems here, the water is pretty much leaking out during the storm event, which is no good. But this red line here is the one with the detention layer. Now I'm going to find it somewhere. I'm very sorry. Okay, simple as that. It's this layer right here. Now, basically that's got 100, between these two layers there's about 100 nylon threads going through every square centimetre. So when the water hits through here, it just takes a bit of time to go through. So it's slowing the water up. Now, it might sound like Mickey Mouse a bit, but this has all been modelled thousands of times in the container model that we have. And it's adjusted with all different types of soil, with all different manufacturers' systems, and that's open. Anybody who wants to do green roof trials can use the same system in the States, and they can put all your data through or whatever. So that's all open there for use. But anyway, that's showing that that water's been detained for that much longer and it's come out slower. So all done. And this is the actual system. So here's one of these beds, and it's been watered. It's in a 1 in 1,000 year flood. The water's built right up over the plant material. The plant material can cope with that for a short period of time, which it is only, because you're only trying to extend that drainage period for that long. You can hear the water running out. That's pretty much that, and then just 1 minute. Sorry, I'll come back to the same one. And so 10 minutes after, pretty much it's dried out. It only has to be 5 to 10 minutes to get that peak discharge to come at a slower rate, which is pretty much the same as what your detention tanks are doing anyway. But here you've got it happening on a green roof. And that's just the water draining out, and you can see the plants are out in the air again, and they'll be quite okay with that. And so we've got, I've had test panels, there's 6 test panels there in Barara and Sydney. I've got 14 test panels at Andreessen's Nursery in Western Sydney. Both of these have been there for more than 2 years. A typical example of and this is without the detention layer. If I get 21 mils of rain, I've got records of 18 months of this, that's 28 litres of water landing on each test plot. Plot number 1 had nothing but drainage cell on it, and we've got 25 litres of water coming out of it. Plot number 2 only had soil, so it's got 10 litres of water coming out. And plot number 3, 4, 5 and 6 have different amounts of the canal urbanscape in them, and 0.12, 4.7, 0.12 and 0.04, sort of nearly zero amount of water coming out of the system. So those test panels are there for viewing if anybody wants to see them at any stage. And then we've also got this software which Knauf have developed where you just punch your roof type in and it'll give you a graph of, so in this case it's how much water will run off your roof versus how much water will be transpired. And this is month by month how that will work. So every month, based on, this one's I think Sydney again, could be somewhere else, but that's exactly the rainfall events and how much water will be released and how much irrigation water you will need on there based on 20 years of climate patterns. And those, the actual PET system key performance indicators for that are energy efficiency, heat island effect, solar radiation, and they give you, if any of you have a building development project, thank you, if any of you have a building development project, they will send them plans and they'll send you all these graphs for your building development, exactly what's going to happen as far as energy consumption goes, heat island effect and water as well. So in this case it's talking about the temperature on the outside of your green roof. That, if you didn't have a green roof, that would be the temperature fluctuations on a daily basis. If you do have a green roof, that will be the temperature fluctuations, and that will indicate to you how much heat's coming off your roof and hopefully helping with the heat island effect in your city. And at the moment, I'm working with Blacktown Council and Western Sydney University, and Blacktown have asked me, okay, well, we've seen all this now, we want our own PhD student, or not PhD, postdocs, to write a report and monitor all this. So we're setting up a system out there at UWS. Over the next 12 months, we'll have these final reports from Australia as well. Although Knauf have them for every city in the world because they've got the climate patterns for every city and it's all dynamic. This is the system we're setting up at UWS. That's the big container there that they've got the test panels in, and we're just going to be having this system here is set up in Singapore, United States and Slovenia, and now we'll have it in Western Sydney, and they're actually all connected digitally from data, basically all the data from all of these, every rainfall event is going together to add up to show what we can do. And here's a job which we're just building. This is at Manly, so putting down drainage cell, we're putting down the canal insulation, urbanscape, we're putting down irrigation, we're getting ready for planting. And that's it planted out, putting soil on and so forth, me and my wife. And so green roofs generally, Rooftop Farms in Brooklyn, fantastic amounts of fruit and vegetables grown. 50,000 pounds of fruit and vegetables grown on that roof every year. Lots of local food production. This is in Chicago. This is emulating prairie habitat on a roof at Chicago City Council. So these are the sorts of, that's all biodiversity that you do, and that's what I do. And so what I've got for everybody in a bag, which is over there, is I've got a model here of the green roof with the green product in it. So there's your plants with the cardboard. There's the insulation wool, there's a drainage layer and waterproofing in there. So there's a little kit in there for everybody if they want one. And it comes with a great book that's all about it. and product specifications and a writing pad from me. So that's what you've got, and they're all there for you. I don't know, any questions or my time's up?
30 seconds to go.
30 seconds. Thank you. Go for it. Well done for it. Anybody want to know anything? I mean, I'm here for a while, so.
It's great.
Oh, no, great.
Just that nylon strip, is there a risk of that blocking or?
No, because it's got the mineral fibre right above it. This stuff is a fantastic filter, and I mean, I've done a lot of experiments with this now. The water that comes out of here is like it's very clean. If I don't have this product in there, I have a lot of dirt coming out, and the water's dirty when it comes out. But when it goes through this, the water's crystal clear. I'm not talking about nutrients or anything, but it's crystal clear, and it won't block this.
What about that blocking? The actual the wool.
The wool. Well, green roofs, the answer to that is green roof growing media, if it's done properly, and you need to do this properly, has no fines in it. So in Europe, in Germany where I worked over there, it's just 100% crushed brick with no fines. Here we use a number of other things, we use a bit of compost as well, but no fines. So you don't have anything that could potentially block anything, and that's the way to do that.
Well,
yep.
It's impressive. Can you just jump back to slide 38? I think it was. Yeah, it's super up to the blue and.
This one?
Yeah, that's like 69.
It says 200 and.
Retained water.
Hang on, should I say it?
No, you can't say it.
And is that, so you think that's a city?
Look, I've just.
That's quite
Let's talk about that after. I'll get that slide open up. I can't see it on here, and I'll tell you the results. But I've got pretty much hundreds of these graphs from all over the world at the moment.
Yeah.
I'm not sure which one I put on there. Looking at that now.
Yeah. And I noticed another figure. 45 to 100 kilograms per metre squared. Is that fully saturated?
So fully saturated. My estimate is I go between 100 and 150 kilos a square metre fully saturated. And that's because I tend to use a little bit more soil. I'm a horticulturist. I just like to give the plants everything that they need. I have, on one of those jobs, I had it down to 45 kilos a square metre on one of my test panels by having 15 millimetres of soil on top of 40 millimetres of that. And that was a 45 kilo build-up. I can guarantee you that will work. The range of plant material will be lower. You'll be able to grow things like pig face and what have you, succulents in there, and that's it. So that's the.
And is it suitable for lightweight industrial structures like?
Yes, it is, but you've got to remember it's 100 kilos. Say it's 100 kilos saturated weight. You might need to put on live load, which is a man walking up there or a woman walking up there occasionally, doing a little bit of maintenance. So you need to calculate that in, and then we need to talk to the engineers and make sure that they've got the right structural elements in there to cope with that.
Is there any water quality benefits to
water quality there's definitely a benefit. That's some of the work that we're going to be doing with UWS to prove that. I mean, we're going to reduce nitrogen. We are going to take out heavy metals and pollution because they're going into the soil. They're going into, and I put a bit of organic matter into the soil like compost. Those microorganisms in there are doing stuff. So we are yet to calculate the actual effect of how much less heavy metals or certainly any pollution that will come out of there.
I'm a bit excited about that, but so 69% retention in stormwater means at least 69% of the nitrogen in your rain.
Yeah, sorry, that's a very good point. The main thing is that there's so much less water coming off your roof. Now, talking to Mark Lieberman from Blacktown, the biggest problem those guys have got is they've got 8 hectare subdivisions going on with sheds on the M7 the watershed that comes off there is absolutely enormous. Like the figures that Mark gave me were just staggering. 8,000 cubic metres of water a second or something. I don't know, massive numbers. And we're going to cut that back by 60%.
I'm also interested in the vegetation. I really like that local community. So looking at the slides that you had up there of horticulture, is that something that is widespread, like it's a common use of these roofs as well?
Overseas, definitely. I mean, I've worked around the world. I was very lucky to be working in a lot of countries, and it's just huge. It's a big market over there. They're all doing it. And places like Stuttgart, you just cannot build a building without it. There's no DA's approval unless you've got a green roof.
And is it because it's that focus and then that might negate any of the other outcomes that
Stormwater drives it,
yeah.
but then biodiversity, views, buildings just look so much nicer. They've got a lot of mountains in Germany, so there's lots of villages up in the mountains, and they look down in the valleys where all the factories are. Well, all those factories just look like a farm now. You can't tell the difference between a canola crop and the rooftop of Ford in one place where I went to. It was just beautiful.
Yeah, sounds
Yeah.
great.
All right.
Yeah.
Thank you.
Okay, so that's gone.